Picture this. You're standing in the freezing north, questioning all your life decisions, when suddenly, boom! The sky starts glowing like someone installed RGB gaming lights across the atmosphere. Green waves ripple, purple curtains shimmer, and you're thinking, okay, who hacked the sky? But what if I told you that this mind-blowing light show isn't magic, isn't aliens, and definitely isn't a glitch in the simulation, although honestly, it feels like one. There's a wild, very real scientific reason behind this cosmic party. I'm Professor Everything, and today we'll be answering the question, how does the Aurora Borealis form? Right here on Explaining Everything. Let's start simple. The Aurora Borealis, also known as the Northern Lights, is a natural light display that happens in Earth's polar regions, specifically the northern magnetic areas. The southern version is called the Aurora Australis, but we'll let Antarctica keep that one. The aurora is basically the sky showing off, a giant, colorful, cosmic dance that lights up the night in shades of green, red, purple, and occasionally blue, like the universe couldn't decide on one aesthetic. Here are a few quick factual details to ground us in science. The Aurora Borealis occurs in the thermosphere and exosphere, roughly 100 to 300 kilometers above the Earth's surface. The lights can stretch across thousands of kilometers and last anywhere from minutes to hours. Ancient cultures had their own explanations. Vikings thought they were reflections of warrior shields, while medieval Europeans thought it meant bad weather, or worse, bad taxes. And yes, there is a literal auroral oval, a donut-shaped ring around the poles where auroras most commonly appear. Earth basically wears glowing space donuts. In short, it's a breathtaking natural phenomenon caused by forces way bigger than us. But what forces exactly? Time to peel back the cosmic curtain. To understand the Aurora Borealis, we have to look at the sun, which is far more dramatic than it appears from Earth. The sun constantly sends out streams of charged particles called the solar wind. These particles, mostly electrons and protons, race through space at incredible speeds. Most of the time, Earth's magnetic field blocks them, acting like an invisible shield wrapped around the planet. But the magnetic field isn't the same everywhere. Near the north and south poles, the magnetic field lines curve and funnel inward, creating natural pathways where solar particles can slip into the atmosphere. Once these particles reach the upper layers of Earth's atmosphere, roughly 100 to 300 kilometers above the surface, they collide with atoms and molecules, mainly oxygen and nitrogen. These collisions energize the atoms, temporarily boosting them into a higher energy state. But atoms don't hold on to that energy for long. When they return to their normal state, they release the extra energy as light. Billions of tiny flashes blend together, forming the glowing curtains and waves we recognize as the aurora. The colors depend on which atoms are involved and at what height the collisions occur. Oxygen at lower altitudes produces bright green, the most common color. At higher altitudes, oxygen can create deep red glows. Nitrogen adds purples, blues, and pinks. The constant shifting of the solar wind and Earth's magnetic field gives the aurora its movement, making it look alive. An enormous, shimmering light show powered by physics itself. Although auroras are silent to the human ear, some people have reported faint, crackling or rustling sounds during the strongest events. While extremely rare, these sounds may be caused by electrical charges building up close to the ground. Other planets, like Jupiter and Saturn, also experience auroras because they have strong magnetic fields and thick atmospheres. Jupiter's auroras are so powerful that they could outshine the entire night sky on Earth. Certain colors, like pure red auroras, are rare because they require specific atmospheric conditions and high-altitude oxygen. When they appear, they tend to look eerie and otherworldly, like something straight out of a science fiction film. The brightness of the aurora also depends on the solar wind's intensity. During particularly powerful solar storms, the auroral oval expands, allowing people much farther south to witness the lights. Historically, auroras have been seen as far south as France, China, and even parts of the Philippines during major geomagnetic events. Modern cameras are more sensitive to light than human eyes, so photographs of auroras often look more vibrant and colorful than what people see in person. This doesn't mean the aurora is faint. It just means our eyes need time to adjust in low light, while cameras have no such struggle. Either way, the experience of seeing the real thing is unforgettable. The Aurora Borealis forms when charged particles from the sun stream toward Earth, slip into the atmosphere near the polar regions through openings created by Earth's magnetic field, and collide with oxygen and nitrogen atoms. These collisions energize the atoms, and as they release that energy, they emit the gorgeous colors we see dancing across the sky. It is a breathtaking partnership between the sun's raw power, Earth's magnetic shield, and the chemistry of our atmosphere. The aurora is nature's own glowing masterpiece, a reminder that our planet is connected to the cosmos in extraordinary ways. So, the next time you see the sky light up in green or purple, you're watching the universe perform a show millions of years in the making. If you enjoyed discovering how the Aurora Borealis lights up our skies, make sure to like this video and subscribe for more fun and fascinating science. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. If you enjoyed this video, please check out our other bingeable channels. Thank you for tuning in, and join us next time here in the channel that answers all the why, what, who, where, and how questions you've always wondered about, here on Explaining Everything.